So, welcome to the next lecture of nuclear chemistry. So, I already talk about that what we will discuss in the next video, that is the nuclear stability. Okay. So, the nuclear stability basically is a very vast thing and very important thing. So, among the whole nuclear chemistry, all of the questions basically, vast of the questions basically depends upon this thing, nuclear stability and all. That's why I thought instead of making one video, I will make two videos. Okay. So, in this part, today this part, I will discuss about the type of stable nucleides. So what are the characteristics for nucleides being a stable? And the second part, we will talk about the reasons for stability of nucleus, like packing fraction, like mass defect, like nuclear binding energy per nucleon, and all the things. So in this part, I will talk about I told you the characteristics of stable nucleides. Okay. Now, tell me one thing. So, nuclear chemistry is full of examples. Okay, I can tell you the concepts, and along with the concept, you should know the examples also. Because if you know the examples, so looking upon the examples only, you can tell the things. So that's why it comprises of a hell lot of examples. That's why I have written down some examples. So I'll use this copy for that thing. Okay. So let's start without wasting the time. So, at first, the stable nucleides are those nucleides. So there are some 2-3 characteristics of stable nucleides. The first thing is stable. The Harkins. There is a scientist called Harkins. Harkins, he gave a rule for a nuclide being stable. So what was this? So he told a nucleides which has even number of proton as well as even number of neutron, these are the most stable nucleides. Okay. So what he told? Even number of neutron, I am writing neutron as N, and again even number of proton. So which nucleides have even number of neutron and even number of proton, these has exceptionally high stability. So that was his verdict. So how he got that verdict? So because if you he actually thought of that whatever nucleides are present, whatever atoms are present in earth crust, okay, so which is present in the most percentage, that will be very much stable. That's why it is present. So that he got that inference, he got that observation, and he inferred that even number of neutron and proton that are exceptionally most stable. Okay. So according to the abundance, I have a chart. Like he has that chart, so I will write down the thing. So neutron, I am writing. It is proton, I am writing. And again, this is the abundance. Okay. So when neutron is even, proton is even, that time it is like 85%. When neutron is even, but this is odd, that time it is 30%. So one more permutation is there, that is neutron is odd and proton is even. That time it only consists of 2%. The thing, that is both neutron and proton, both are odd. So he told both even is very stable. So that means both odd, that is the least stable. So the percentage is almost negligible. Abundance is present in earth crust, not all the place. Okay. So this is the thing he told. Now, this is called Harkins rule or Harkins Oddo rule also. So from this, so now let me give you some example. Right. So oxygen, what is the atomic number? That is 8 and mass number 16. So proton number, according to the representation, I can write it down here. So this is again 8. So 8, this is even, and this is even. So even neutron and even proton. So this is exceptionally high. Okay. So almost, I think, if I am not wrong, that is 48% of earth crust is made up by that oxygen isotope. Okay. So you can easily see this thing. Now, let me come to the next point. So this is according to Harkins. I told you this is Harkins rules and as well as Harkins Oddo rules. But Oddo itself give one more characteristic as a rule. That is called only Oddo rule. What it tells? Oddo rule, it tells like nucleides, okay, listen carefully. Nucleides which have mass number which is multiple of 4. Okay, nucleides which have mass number multiple of 4 are exceptionally very much stable. So A, I am writing in a mathematical term like A is 4m, where m is nothing but the natural number like 1, 2, whatever. So nucleides which have mass number multiple of 4 that are exceptionally stable. And to tell this, like nucleides in nucleases, I already told you nucleides is comprised of neutron and proton. So if you know that alpha particle, that was also I already explained. Alpha particles are 2 neutron and 2 proton. Okay. So as this is nucleus comprised of 4, he told like this is comprised of alpha particle, like this is comprised of alpha particle. So the nucleides, these have the building blocks as alpha particle. Okay. So alpha particle you can easily show the mass number will be 4 because 2 neutron, 2 proton. So the nucleides which have 4 multiple mass number that are alpha particle nuclei, and that's are very much stable. So let me give you one example. Again, that example also that is comes under that Oddo's rule. So this is 14, that is 4 into 4. That is a multiple of 4. Okay. So these are the things. Now one more thing I want to tell, that is in less atomic number region. Okay, in less atomic number region, if you add, like if you take one nucleides in less atomic number region. Okay, let me take this again, 16. So if you add a neutron, then a proton and a proton in this order. Okay, what I told, neutron plus proton plus proton. Okay, if you add one thing, so whatever the nucleides you will get, that are stable, and the final nucleides, that will be again 4 multiple mass containing nucleides, and that will be exceptionally stable. So if we add 1 neutron, what will happen? Neutron has 0, 1, so mass number will not change, that is 7. You know oxygen also has this isotope. Now again let me put this at neutron. So what will happen? 18, oxygen 8. That is also available in, like, available. That is also available. Now 1 proton. What will happen? Proton has 1, 1. So that will be oxygen. Fluorine 9, 19. That is it. Fluorine has only one isotope, that is this. So this is also stable. Now one more proton. What will happen? 10, neon, and 20. And this is inert gas. Like inert gas type. In case of electronic configuration also, this is very stable thing, as this is an inert gas, and in this case also it has 4 into 5 type of mass number. So this is very much stable. So the thing is, they are telling alpha particle building blocks nucleides that are exceptionally stable. So whatever, like how they are telling, if you add a neutron, proton, then you will get exceptionally stable moiety, because you are adding 4 now. 2 neutron plus 2 proton, so mass number will increase by 4. That's why. Okay, so that are the things. Now these are all the characteristics. One more important, not that much important, but information should be there always with you. So the thing is, in low atomic region, again, in low atomic region, if A is even, listen carefully, okay? In low Z, I'm writing Z, so low atomic number region, if A is even, that time, that nucleides have 3 isotopes. If A is even, that has 3 isotopes with mass number A plus 1 and A plus 2. Again, the example I can take, oxygen 816. What are those other isotopes? That is again 17 and 18. Okay? And if A is odd, that time these nucleides will obviously be a monoisotopic nucleides, but in low Z region. So A is odd. Now let me take one example. This is 8. So fluorine, okay, 9, and this is 19. It has monoisotopic nuclides. So these are some characteristics of nuclides. Again, one more very important thing you have already heard about, that is magic number. What magic number is? So what magic number is, to tell is, you already like whole of the chemistry you know so far, that is basically deals upon the electronic configuration, electronic structure and all. So now we are reading nuclear chemistry also. So now in case of electronic configuration, you know the some number of electronic configuration that are inert atomic configuration that are exceptionally stable. So what are those numbers in case of electronic? I'm telling. What are those numbers? 2, 10, 18, 36, 54. Okay. Now, like this. So if these are the electronic configuration, that time the atom are very much stable. Like this in case of nuclear also, there are some numbers. If your neutron or proton number has this configured, like if your neutron or proton number is this, that time this will be very much stable. So what are those numbers? Let me write down these things. That are 2, 8, 20, 50 and 82, 126. Okay. Now the thing is, if your nuclides has a proton number of magic number or a neutron number as magic number, that time those nuclides will be exceptionally stable. Okay, so what I am telling, if your nuclides have proton number as a magic number or neutron number as a magic number, that time these nuclides will be very much stable. Now, a very simple question you can ask, like it can arise in your mind, that if your neutron and proton both have that magic number configuration, then what happens? So then that will be exceptionally high stable, like that will be more stabler than if it contains only neutron as a magic number or only proton as magic number. So the thing is, if I'm again writing it for you, like if neutron has a magic number or proton as magic number or both magic number, then these are very stable. So here one question may form, like if they are giving 4 nuclides, okay, they are giving 4 nuclides and telling which among these which one will be the most stable. Okay, so let me write down one question for you. So I have written down 4 examples. Okay, so what type of question they may ask? Like they are giving these 4 nuclides and they are asking you, among these 4, which one will be the most stable? Okay, now let me come one by one. In case of fluorine, okay, it has atomic number of 9, it has mass number of 19, so the nuclide, like neutron number, that will be 10. Now in case of barium, it has atomic number of 56, it has mass number of 138, so what will be the neutron number? That will be 2 and that will be 82. Now for this case, helium 2, 4, that means neutron will be 2, and this case it will be 10. Okay, now it's okay. So these are the things. Okay, but sorry, here is a mistake, that is 50, it will not be 50. How can it be? It will be 90, so this will be again 50. Okay, now among these numbers, which are the magic number? That you need to know, like that you need to find out. So come to this thing. Does this have any magic number? 9, 19, 10? So no, it don't have any. In this case, 56, 138, no, but 82, yes. So it has a neutron, I am writing, n is magic number. Now come to this. It has 2, both, like it has neutron number as well as proton number, both are magic number. So n and p I am writing. in this case, that is 40 and 90, these two are not magic number, but 50 that is. So again, it has one magic number in this as its Neutron number. So among these four, I already told, if neutron and proton both magic number, if neutron and proton both are magic numbers, so then that will be the most stable. So this is the most stable thing. So if you give you the four, I am just taking one example. They can frame this question like in 1,000 ways. Whatever may be the thing they can choose and permutation, combination, they can come up with some question. But the concept should be like this. If it has both neutron proton as magic number, then that time that will be very much stable. If it has only one, if they don't give this one, but rather than they give the three as three atoms, it's like three nuclei which don't have any magic number, but one I have. So that will be the stable. So you are smart guys, you can do this thing. Okay. Now these are all the characteristics thing. I already told that some rules and magic numbers and all. Now let me come to the most important part of this chapter. What is this? Most important part is this, the NP ratio. In some places that is written as N by Z also, because it's the in the representation only we had told A, Z and N. So that's why some places that is written that is N by Z. Some places it is written N by P ratio. So we will not follow this N by Z. We'll follow the N by P because it sounds good, na? Neutron and proton, the N by P ratio. Okay. So scientists they took a survey of proton and neutron. So with the proton number, how neutron number is varying. That's the thing. They have made, like they thought there will be some correlation between the proton and neutron. Okay. So whenever they took the survey of proton with the proton number, how neutron number is varying, they come up with a plot that is almost a straight line. Okay, almost a straight line. They thought it will be 45 because with the number of proton, neutron should increase in a linear way, but it is not that much good linear way. But that the angle is not 45 degree in experimental case. It is like it has some deviation from the 45 degree linear straight line. So this is the thing. So here proton, this is neutron. So I already told you. So variation of neutron number with proton number, that is a chart they got, and the name of the chart, that is also important. That is CSIR chart. Okay. So pardon me for the marker. It's not working for it. So this is called CSIR chart. Okay. So what is CSIR chart is the chart of neutron number with proton number. So now if you can see this thing, that in low atomic number region, proton number means atomic number also. So in low atomic number region, it is following the 45 degree line. So the 45 degree line I am telling you every time what this is. So if a straight line is giving N by P is giving 45 degree line, that means N by P is 1. Okay. So that means in low atomic region, the N by P ratio, that is 1, and that's why it is following this straight line. But after a certain number of atomic number, it is not exactly giving N by P as 1, but rather than it is giving N by P slightly less than 1. Now, let me point out some very important things. What are those? First one. Up to Z is equals 20. N by P is equals 1. Up to this is 20. Now, after 20, N by P is greater than 1. I already told you. N by P is greater than 1 and it can reach up to 1.6. Okay. So you will wonder why N by P ratio is increasing after Z is equals to 20. This the reason is not completely clear, but there is an explanation. There is a thinking that maybe this is the reason. So what is this? these are important, so that's why I am erasing this part. Okay. So what is this? That thing is, at time they are telling, okay, if Z is increasing, okay, that means Z means proton number also. So proton has a charge. Okay, Z is increasing, that means proton is increasing, that means charge is increasing. So the Coulombic repulsion. Coulombic repulsion means the repulsion between two charges. The two same amount, the same type of charge if comes along, then that two will repel. But if the two not like plus and minus will come, that time that there will be attraction. But protons are increasing, and in nuclides there is only charge particle, that is proton. Neutron has no charge. So along with number of increasing of proton, the Coulombic repulsion that is increasing. So if Coulombic repulsion increasing, that means the stability of nuclides is somehow decreased. Sorry, it will somehow decrease. So the scientists have thought that to overcome that repulsion, some extra number of neutron should be there. Okay, so that is the reason to overcome the Coulombic repulsion, which is due to the number of increasing of proton. We need some extra number of neutron. So I told you that N by P ratio. So if N increased, that means it will obviously go to higher than 1. That is the thing. So it can reach up to 1.6. Now, the number 3 point, like, I think you have written down the things, so I am erasing all the things. This graph is also, I am erasing. Now, after 3 points, after Z is equals 83, the N by P ratio is greater than 1.6 also, like it will increase, and then these are not stable nuclides then. Now the thing is, you need to think that if N by P ratio, like if our nuclides is below or above the N by P ratio, if a nuclides is below or above the N by P ratio, that time that will be unstable. So the nuclides should follow the signature with the N by P is equals, like N by P is whatever the N by P ratio is, 1 up to 20 and 1.1 to 1.6 up to 83. So it should follow this. If it is less than that or above than that, that time it will be unstable and it will do something to get that N by P ratio back. So these are the main points of N by P ratio. But if you know the N by P ratio, if it is greater than or less than, that time you can predict that it will undergo which type of emission, like beta emission or neutron emission or whatever the thing. So we will discuss these things now. So now, at first, if N by P ratio is greater than the range, if our nuclides have N by P ratio greater than range, so what will happen? Now, this is my N by P. Now it is greater than the range. So we need to decrease this. To decrease this N by P ratio, what do we need? So if we decrease this thing, okay, if we decrease N, then also N by P ratio will decrease and it will come to the stable range. And again, if we increase the P, that time also it will go to the, like it will decrease and it will go to the stable range. So we have two options, that is neutron, one neutron should, like one neutron should decrease or one proton should increase. So how it will be? There is a two possibility. One, directly neutron emission. And the second is one proton is converting in, one neutron is converting into proton. So if one neutron is converting into a proton, that time one neutron is less and one proton is increasing. That time, so that will N by P ratio as a whole, it will decrease and it will come to the stability range. So that is called beta emission. Okay, So we'll discuss two things separately. Now I will tell first neutron emission. If one neutron emits, so what will happen? So let me take this example. Krypton 36, 87 to 1 neutron is emitting. That means 1 neutron. Okay, 0 1. So 1 neutron if it emits, so mass number will change by decrease by 1, but the atomic number it will not change. So that will be 36. If atomic number is not changing, that time the atom will be obviously be krypton, and it will change by 1. So it will decrease 1. It will be 86. Now that will be, what is the proton number? 51. So N by P ratio, that will be 51 by 36. It will become around 1.41. Now 8 has 0 and 5. It is 50. So what will be the N by P ratio? 50 by 36. So now if I don't know the calculation also, then also you can show, like you can see that is 51, there is 50. So it will obviously decrease. It will be around 1.39 and plus 0, 1. So in this case, you need to know the thing. Any emission thing or any nuclear reaction, the mass number in LHS, like left hand side, and mass number in RHS will be same. Like after emission, and like in this thing, this will be the same of this plus this. And again, the atomic number or the proton number also will be same in both side, left hand side and right hand side. So I will write down the thing properly. I am just telling now. Energy will also be same. Nuclear spin will also be same in all like nuclear emission. So this is the one of the examples. So 1 neutron is directly emitting, and we are getting somehow N by P ratio less than the what it had before. So this is, but neutron emission is not that much feasible, because neutron emission has a very high energy requirement, almost around 8 mega electron volt. Okay, so that's why it is not that much feasible. Now come to the most important thing, that is beta emission. That is, I told you, beta emission. Sorry. So I told you there is a N by P. So if 1 neutron converted into 1 proton, that time again N by P ratio will decrease. So this thing, if 1 neutron is converting into 1 proton, that is called a beta emission. So how it is? Now let me write down. I am telling that is 1 proton. Now what I told, in both side, mass number as well as atomic number, that will be same. Now it has 0, it has plus 1. So what it should be? There should be a particle which is minus 1. Minus 1 atomic number. So if it is a minus 1, and again it is 0, it should be 0 because this is 1, there is also 1. So it shouldn't have any mass. So now if a particle has 0 mass and negative charge, that is obviously the electron. Okay, we are talking about the elementary particle. So that is electron. Now the story doesn't end there. So what are the thing? We need one more particle, that is called beta particle. Sorry, anti-neutron particle. So you can remember this thing, like electron has a minus, there is a minus charge, also there is a bar. So whenever there is a minus charge is there, that time it will be bar, and it is called anti-neutrino. Neutrino. So this is a particle, it is coming because of the energy state. Like I told you, not only the mass number and atomic number are going to be same, as well as energy, as well as nuclear spin, as well as statistics, all the things will be the same before and after emission. So that's why this particle is introducing. It don't have any mass. You can see it from this, no mass. Okay, but it is coming due to the equalizing the energy thing, the nuclear spins thing. We will discuss this after all of the possibility of emission over. Okay, we will discuss the things. So this is 1 neutron. It is converting into 1 proton, and along with that proton, 1 anti-neutrino particle is coming out. That is the thing. Now let me take one real life example. That is 14 C6. Neutron number will be 8. N by P ratio will be 8 by 6. Will be 1.33. Now, one neutron is changing. So what will happen? One, like from 0, it is coming around +1. Because this is ejecting. So this thing will increase because there is a +1 from 0, that is +1. So that will increase to 7. So if this is 7, what will be the atom? Obviously this. And now this will be 14 again, and this will be 7. So what will be the N by P ratio? 7 by 7, that is 1. So from 1.33 we are getting 1. So N by P ratio is decreasing. And along with that I told you one beta particle, that is the electron, and one antineutrino particle. That is the thing. Now this is the two possibilities for if for the case N by P ratio is greater than the stability range. Now I hope you have written down the things. I am giving you some 2-3 second time. Again I will write down the other things. So you can write down this thing. So now let's talk about if N by P ratio is less than the range. Range means I am obviously mentioning the stability range. So if N by P ratio that is less than the range, so what will happen? Now again we have N by P. So it should now increase. So one neutron, like we need N. We need N increasing. That means one proton can transform into one neutron. Okay, then N will increase and proton will decrease. That time again N by P ratio will increase, and other possibilities I will discuss one by one. Now let me erase the thing. I hope you have written down the things because these are very important. So I told you that one proton will convert to one neutron to increase the N by P ratio. Proton, if it transform into one neutron, then what will happen? It has a +1 and it has 0. So there will be obviously a +1 particle, and mass are same. So that means that is 0. So this particle, that is called as, like, this is not the charge plus. So neutron plus this particle. So this is called, like this, you can see in case of beta particle, that is -1 and 0. In this case, this is only +1 and 0. Everything is same, mass is same, only it differs in charge. So this particle, that is called electron, and that's why this is called positron. You can, so these are only the positive charge, that's why it is positron. Now the thing I am already discussing, that is because it has a positive charge, that you don't need to remember the thing, you can obviously remember that is positive, from positive it is coming, that is positron. So this is the thing. Now that's what the possibilities are. Positron emission. Okay, I am not writing all the things again and again, erasing and discussing. I am write one and I will discuss. So let me erase this thing. So let's come to the positron emission. I already told you, from one proton will transform into one neutron. So it will obviously eject one positron, and again one particle. It will come to equate the energy, the nuclear spin, nuclear statistics and all. So sorry, in that case there will be no, because this is a positive, so no bar is needed. Like this is not the case. I am just telling you to remember the thing very easily. I remember this thing like this. Okay, so this is the thing, and so this is the story. Now let me take one real life example. So what is this? I have written down the thing for you. Neon 10, 19. I am not writing down the N by P every time, because you can just easily go and you can write that is be 9 by 10. So it will obviously be less than 0.1. Now from this +1 it is 0. So that means obviously one atomic number or one proton it will decrease. So that will be 9. So 9 means the atom is fluorine. Now mass is same. So mass will be 19. That is 10. You can N by P ratio obviously increase because 10 by 9. and one positron particle and the neutrino. So this is the example. You just go by your own. What is the N by P ratio? It is 0.9. It is increased obviously. So this is the thing. Now it has also a high energetic barrier around 1.02 mega electron volt. Because of that, because one like positive charge is in ejecting, so this has a very high Coulombic potential barrier. That's why it has also energy requirement of 1.02 mega electron volt. So this is the thing. So just the same thing, but it has the less energy requirement. That's why one more possibility has arises. What is this? That is orbital, okay, electron capture. Orbital electron capture. So I have written down from one proton it is transforming into one neutron. Okay, one proton it is transforming and it is giving a positron. Sorry. Now instead of this, if we add, that I have written again this one. Now I am adding this thing in right hand side. Instead of writing this right hand side, if I write it in left hand side, so what should be the particle to get neutron? I need one neutron. So if we can add obviously a electron. Okay, now because 1 minus 1 that is 0 and 1 0 that is 1. So if now the thing is, the story is like this. So there is a proton. Like there is a coarse thing. There are some orbitals and all. So if this, there is a proton, their protons are residing in there. So if these nuclides take one electron from here and undergoes this thing and form a neutron. So that time, so proton is taking one electron and it is forming a neutron. So that time there will be a vacant site because one electron is already captured by the nuclides. So now here also very much like number of new electrons are there. So from a higher orbital, one electron will come to stabilize this vacancy. So one electron will come. Now from a higher energy level, electron is coming to the lower energy level. So energy will radiate. So in this energy, this is called as X-ray, characteristics X-ray. And again, this energy, if this energy, whatever it is ejecting, that can again strike out one more electron. So there are two possibilities. One is electron is coming from the higher level to lower level and energy is ejecting. That is the characteristic X-ray. And when whatever the energy that is ejecting, if due to that energy one electron is again strike out, that time that is called Auger effect. Okay. So this is a very important thing, and just like due to the two things, there is a very vast spectroscopic literatures are there. Spectroscopy, a whole lot of new spectroscopy has been generated with this X-ray and Auger effect. So I'm not going through all the things. So these are the two possibilities, that is orbital electron capture. So I'm erasing the thing and let me give you one example. So let me discuss the orbital electron capture. Okay, I'll take one example. The thing I am writing again. So one proton, it is taking, one electron, and it is giving neutron. And again to equate all the things, it will need one more neutrino particle. So I told you now, whenever that is like there neutron, so that means it is a neutron is coming. This is the thing. So when orbital electron capture is happening, so there is a positron and there is orbital electron. So there is almost the two things are same, but I told you positron has a higher energy requirement. But when that much energy requirement is not there, that time to get the N by P ratio, increase the N by P ratio, that time orbital electron process will happen. So let me take the example. Example is Mn 25 54 plus one electron is capturing, so 54, because this is same. Now it will decrease because this is negative, so that will be 24. So 24 is chromium plus neutrino. So this is the thing. Now N by P ratio, I am not again reading it over and over, so you will just find out the thing by your own. So this is the example. Other is, that is alpha emission. So if alpha emission occur, that time also N by P ratio will change, because alpha is like a helium with 2 and 4 mass and 2, like 2 neutron and 2 proton is emitting at a time. So let me take one example, 92 to 38. So proton is 146, I think. Okay. So N by P ratio is 1.58. Now plus 1, sorry, alpha, that means alpha means 4 will decrease and 2 there will be decreased, and that is 90, and that will be 234. So that is thorium plus 4Hu2, that is the alpha. So again, what will be the that is 144. 144 by 90, that will be 1.60. So for 1.58 it is increasing to 1.60. That is one of the example. Now one more example, like one more possibility, that is directly a proton emission. Because N by P, again you can just go by this. If one proton emits directly, like that, they are in that case neutron emitted. So if one proton emitted, that time proton N by P ratio as a whole, it will increase. So that is the reason. So, but proton emission is not that much favorable because of the higher energy requirement, because proton has a charge. So whenever one charge is there, that time Coulombic attraction potential, Coulombic barrier will be there. So proton emission, there's a possibility, but it is not that much visible, that much possible because of the higher energy requirement.